In the first part of this video lecture, we have already introduced the extended real numbers, how to do operations with those elements and properties that these operations have. We discussed what is the devil and this theory, which is plus infinity minus infinity. And now we're going to talk about infinite sums and to discuss the two overlapping measure and integration theories that are studied. So we have seen that we'll be working with this set that extends the set of real numbers by adding two elements on it, properties that we can define, operations that we can define there, properties that these operations would have, that they are very convenient, and referring you to external material for the complete definitions. We have defined 0 times infinity to be 0 just for convenience, and we have discussed several caveats from the theory, cancellations that no longer work, and some limit rule that no longer works as well. We have emphasized very strongly what we do not want to see in this theory, so now we are ready to move on and discuss infinite sums. So how do we compute an infinite sum? So if we have a collection of numbers x indexed by some parameter alpha. This alpha doesn't need to be in a set which is ordered or not even countable. It's just a collection of numbers. They can be repeated, so that's why I'm indexing them by some numbers in some index set. They are non-negative. They are allowed to be plus infinity, but they are not allowed to be negative. So we define the sum of these numbers. So this is just at this point just a formal symbol. We're just defining what the sum here means, and it means the following. We take a finite subset or a finite number of elements from this collection. We compute their sums. This is fine. We know how to add finitely many numbers. There's no problem here. And now we take the supremum over all possible choices of finite sets from this large set here of indices that might in principle even be uncountable. Let me emphasize once more. This is a very robust definition. It is very convenient, okay? And it means in the non-negative world, any collection of numbers can be summed. It does have a sum. Of course, the sum can be plus infinity, the sum can be 0, the sum can be anything. And this is very convenient. And we can, if we take now a different collection of numbers and we compute the sum of that collection, then the sum of the sums will be this will have properties such as this one. And now that we know how to add an arbitrary collection of non-negative numbers, now we can add a collection of any types of numbers. So if we have an index set and a collection of numbers indexed by that set of extended real numbers, then we can define the sum of all those numbers as follows. For each of those numbers, we split it into its positive part and negative part. If the number is negative, the positive part will be 0. If the number is positive, the negative part will be 0. This is how we define these two little symbols here. And if the number is 0, then both the positive and negative part will be 0. So once we split each number into a positive part and negative part, now instead of having one collection of numbers, we have two collections of numbers, and they're all non-negative. The first one is the positive part of the numbers. Second one will be the negative part of the numbers. And then resorting back to the previous definitions, we can define this sum. Once they are defined, we can compute their difference. So here we compute their difference. This is, of course, as long as the above expression does not give plus infinity. So as long as these two sums are not both infinite, we can compute this difference, and we can call that the sum of these numbers. Now, if our index set is countable, that we can just suppose it's the set of natural numbers. And when we're summing a collection of numbers indexed by natural numbers, we can think of that collection as a sequence, and now we're talking about a series. And it turns out if that series is absolutely convergent, and that's important, if it's absolutely convergent, then the summation will coincide with the definition we just gave. And that means, in particular, I'll let you think about it, about why. In particular, this means that absolutely convergent series, they can be reordered at will. We can reshuffle those numbers, and when we add them, we get always the same result. Let us now talk about the two overlapping integration theories that are considered. We have seen that when numbers are non-negative, the sum is always defined and it has very nice properties. We have also seen that if a collection of numbers is absolutely summable, then the theory is also very powerful and robust in that context. And these two cases, which do have some intersection, which do have some overlap, this division in two cases will be present very often in this theory, and we'll see this very often starting from week 4 of this module. And what is it? It is that there are two theories that work very well. It is when everything is non-negative, and then we take numbers, take values in 0 up to plus infinity, including 0 and including plus infinity. And another theory is the absolutely integrable or absolutely summable theory, which involves quantities taking values in real numbers that can be both positive or negative. Okay. We'll see now just some quick examples to illustrate these two facets of measure and integration theory. The first is TONELLI theorem for series, so that's a baby version of TONELLI theorem. It says if we have a sequence of non-negative numbers, a doubly indexed sequence, so it has two indices here, then if we sum over one index first and then the other, or if we sum over the first index and then the second one, we get the same result. Then corresponding to TONELLI theorem for series is FUBINI theorem for series, which is again a baby version of FUBINI theorem. It says if we have a doubly infinite sequence and now we allow numbers to be negative, we even allow them to take values minus infinity and plus infinity. If the absolute values of this sequence are summable, that already excludes the possibility that any of them is actually infinite. If the absolute values are summable, then we can sum the sequence first by taking the second index and then the first index, or starting from the first index, then the second index. It doesn't matter, we get the same result. And here is a counterexample of a sequence, a doubly indexed sequence that cannot be summed by rows and then by columns, or by columns and then by rows to give the same result. The result will be very different if we sum by rows first and then we sum all the columns that we get. It will be 0. If we sum by columns first and then we sum by rows, we get 1. That's very bad, of course. That's not the type of thing we want to handle in this theory. And so what is the sum of all these numbers? We cannot define the sum of all these infinitely many numbers indexed by pairs of natural numbers. So what is the sum of these numbers? We don't know. We cannot define that. And then you can ask, well, whose fault is this? What is the cause of this sequence being so bad that we cannot compute the sum of all its elements? I'll give you a small hint. Yes. This is the cause of all the trouble, as usual.